Hello everyone, welcome to what will be pre-lecture number 29. We're going to be talking about intermolecular forces today, or IMFs is what I'll be calling them for the rest of the pre-lecture. So, we have different types of intermolecular forces. Something else that I'll actually point out here is most of what we've discussed up to this point in the semester are intramolecular bonds, so bonds between different atoms that we would consider generally to be covalent, especially in something like water, shown here. Intermolecular forces, what we're going to be talking about this week in this lecture, are where we have interactions between two different molecules. So in this example, we have a hydrogen that hydrogen bonds with a lone pair of electrons on a separate molecule of water. And so that dotted line is an intermolecular force or an intermolecular bond. Okay? We have different types. Typically, we refer to them as intermolecular forces. They can also be called van der Waals forces. They're synonymous. They mean the same thing. Okay? The weakest of these intermolecular forces are called dispersion forces, occasionally London dispersion forces after someone named London who found them. We'll talk about more what those look like here in a minute. But those are the weakest intermolecular forces that we can have. Those are going to be present in every sort of molecule. Next up, we have dipole-dipole interactions. And so these are intermolecular forces that are between atoms with different, and we would say significantly different, electronegativities that create polar bonds. Okay, and so that's our next strongest. Next up, and the strongest for covalent molecules, are hydrogen bonds. And so a hydrogen bond, as the name would imply, involves hydrogen, but it is going to be when hydrogen is bound to one of the three most electronegative atoms, which are nitrogen, oxygen, and fluorine. You could also call that the Knopf monster, if that helps you remember. And this is basically a extreme version of a dipole-dipole interaction, where we have a specific set of elements that leads to this very extreme dipole, and thus we call it a hydrogen bond. Otherwise, we also have ion dipole interactions, and so we'll talk about those a little bit. Those essentially happen when we have some sort of ion, some sort of salt dissolve in something like water. We can get ion dipole interactions between the positive or negative ion and the positive and negative partial charges that are on something like water. And we, of course, have ion-ion forces, and those are what we just describe as an ionic bond, where we have two atoms or more atoms held together through electrostatic interactions. So those are different kinds of intermolecular forces. So let's take a little bit closer look at each of them. Again, our weakest are dispersion forces, and they're going to be present in all states of matter. And so because of this, because our electrons, rather, in our molecules are always going to be in constant motion, at any moment in time, an atom or a molecule can develop what we would call an instantaneous and temporary dipole. And so what that means is maybe our electrons are localized on the right side of our molecule, so that right side would become partially negatively charged for just an instant, and the left side would become partially positively charged for, again, just an instant until our electrons continued moving and redistributed more symmetrically. This will primarily be present in larger or heavier atoms. Basically, the more electrons we have, the bigger our electron cloud is, the more likely you're able to, or the more able you are able to see dispersion forces. Typically, things that are light certainly do have dispersion forces. They're just not as evident because their electron cloud is smaller. Then something else to consider here is that when we have this electron cloud, it is said to be polarizable, and that will have a large dispersion force So again, take-home point there is that the bigger a molecule is, or the bigger an element is, the more polarizable it will be. Also, the larger the dispersion force it will have. Okay. All right. So an example of this, what is characteristic for molecules with dispersion forces? Typically, they only involve a single element. So I've listed out basically all of the diatomic compounds from column 17, halogens on the periodic table. So we have fluorine, chlorine, bromine, iodine, and astatine. So they tend to be a single element. They only contain bonds that are nonpolar, so things that have matching negativities. If they're not the same elements, things like hydrocarbons, things that only contain hydrogen and carbon are another example of that. And then they can contain polar bonds, but in a symmetrical fashion. So something like CCl4, where all of our dipoles cancel out to 0. That is another example of dipoles. And something else I want to point out here is we go down the periodic table, so fluorine, chlorine, bromine, iodine, we can see that our atomic mass gets larger, the radius of the atoms gets larger, and that is going to have effect on our physical properties such as melting point and boiling point. We can see those temperatures go up for all of those elements. What's changing there is the magnitude of our dispersion force instead of just the type. Okay? All right. Next up, we have dipole-dipole interactions. And so, as you hopefully remember from a couple weeks ago, when we were dealing with Lewis structures, we have differences in electronegativity that can lead to a partial positive and partial negative being present in a molecule, something that we call a dipole, right? So we could think of a partial positive, partial negative. If we think of the intermolecular force, that partial positive is going to be attracted to that partial negative in some sort of manner. Two examples are shown there, and that is going to make things a bit more sticky. So the polarities, just as a reminder, are determined by the electronegativities of the atom and also the geometry. And so again, if we have a totally symmetrical molecule, our dipoles might cancel out to be nonpolar, and so this has to be a permanent dipole. So these are medium strength intermolecular force. Common characteristics of molecules with these is they must contain multiple elements, so it can't just be a single element. Must contain polar bonds, meaning differences in electronegativity, and those polar bonds must be distributed in a non-symmetrical fashion. So if you think of CHCl3, not all of the polarities cancel out to 0 there. Basically, we would have a partial negative on the side with more chlorines and a partial positive on the side with the hydrogen. Which brings us to our next example, hydrogen bonding. It is an extreme form of a dipole interaction, so we say it's all its own. And it will occur when we have hydrogen bound to a nitrogen, oxygen, or a fluorine, aka the NOF monster. The hydrogen bonds are a very strong intermolecular force, but they are still only about 5 to 10% as strong as an intramolecular bond. So if we think about water, again, our intramolecular bond is between the oxygen and hydrogen here, and that's going to be quite a bit stronger than this intermolecular force between the hydrogen and the lone pair on this oxygen for a different molecule of water. So something to consider, in order to have a hydrogen bond, we need a hydrogen bond donor and a hydrogen bond acceptor. And so your hydrogen needs to be bound to an oxygen, nitrogen, or fluorine in order to be a hydrogen bond donor. So you need NH, OH, or FH. But to have a hydrogen bond acceptor, you just need an available lone pair. So anything with a lone pair of electrons on it can form a hydrogen bond as a hydrogen bond acceptor through the lone pair. So in this case, this molecule is our hydrogen bond donor. This molecule is our hydrogen bond acceptor. Okay. Water is kind of the classic example here, and part of the coolness of water, why it's such a unique molecule, is because it's able to accept and donate 2 hydrogen bonds. And that gives water a lot of the special properties that we know and love about it. All right, that's it for lecture today. I hope that was useful. If you do have any questions, please let me know. Otherwise, I will see you in class.